Okay. Yeah, let's oh, before we get to the material, I have decided or I'm planning to give you the final exam on the first day of like the final the week of the finals, which is December 9th. I'm planning to give you well the whole day that you can choose any time to start your test, which would be still on WebAssign. Actually, our class, if we use the university schedule, it will be scheduled to be December 15th, which is a bit late. And I think I don't want to get conflict with your other courses, finals, if I scheduled at a specific time on December 9th. So you have the whole day to choose what time you want to start your exam on WebAssign, but you have to finish it within like certain time. Right now, I think I put 2 hours and 45 minutes. So you can start it anytime on December 9th and just need to submit within 2 hours and 45 minutes. I feel that would give you more flexibility. Yeah, that's about the schedule of the final exam. Okay, now let's go to the material. Well, let me see. Okay, that sounds good. Okay. Yeah, we still miss one person, but like if you missed what we just said, it's our final exam will be on December 9th. On WebAssign, you can start anytime on December 9th and just need to submit it within 2 hours and 45 minutes. If you have problem with this schedule, please let me know sooner so that I can make adjustment. But I think the whole day would give you enough flexibility to choose. Okay, let's get to this week's lecture. Well, my throat, I got sore throat recently. So the lecture might be a bit shorter for today, but that would be enough, like cover the material for this chapter. I tried to make it shorter so that my throat will not suffer too much. So, well, this week you saw it. We have this 2 sample tests. We talked about hypothesis testing in general, and also we saw, well, where we can apply it. More often it's in linear regression, and you can always see them like show up randomly in like any application cases. But for this 2 sample tests, from my experience, like if you work in industry, especially if it's IT companies, they would give you, I think, like they would interview you about A/B testing, which is very popular. So that's mainly on hypothesis testing, and mostly it's 2 sample tests. So this chapter is sort of important, like for your future usage. Well, not only in industry or in research, if you are in biology, you have to do experiments. 2 sample tests happen fairly often. So you need to use it, and you have to design the experiment and carry out the analysis. So that's just some general thing about these 2 sample tests. So let me get this side. So well, now we switch gear from one sample to two sample. What that means to us, like the question we're answering is moving from asking, is the mean of some group being 7? Is the mean of the group 7? We moved it to the question, is the mean of group 1 the same as the mean of group 2? So now we have two groups, so two sample tests. That's what it is. So we can either comparing, well, yeah, we can either comparing like two different groups, or like two different groups. It can be like case control studies. Does the control group have different mean from the test group? Or we can have the scenario being comparing the measurement before and after some treatments. So this is the keyword. We have control group, treatment group, and before or after treatment. So this is where when we need to use two sample tests. So we learned z-test and t-test. Now we look into two sample tests, two sample z-tests and two sample t-tests. Well, we still have some basic assumptions and like our hypothesis. So we are going to talk about the difference in two means. So the difference being mu1 minus mu2. And a natural hypothesis would be whether the difference being 0. And you can also make a confidence interval around the estimates of mu1 minus mu2. So basically it's a confidence interval for x1 bar and x2 bar. And the assumption we have here, which is the basic settings, where for the first sample, we have m objects. So m elements, x1 to xm is the first sample. And we have mean being mu1 and variance being sigma 1 square. And for the another sample, where the size is n, and we're assuming the mean being mu2 and the variance being sigma square 2, sigma 2 squared. And we're assuming these two samples, they're independent of each other. So this is the basic setting and assumptions about the two groups. So once we have this, we would look at like what estimates we will focus. So first of all, we need to look for estimates for the difference of the mean. So as I said, a natural choice would be like x bar minus y bar. And we can actually guess why do we use it? It's mainly because it's an unbiased estimator, because when you take the expectation of this estimate, you will get back to the true parameter, mu1 minus mu2. So we would focus on this estimate, x1 minus, x bar minus y bar. And now we have the estimate. We need to get its standard deviation. The standard deviation of x bar minus y bar. Where you can look at this, how I get this, just you take the variance of this estimate, because these two are independent, and we can just take the variance of each, and this minus would essentially becomes sum, because we are taking the variance. So this thing just equal to taking the variance for both and sum them up. So we now know that this is the variance of this x bar minus y bar. and then the standard deviation, you just take the square root of the variance. So this is how we get the standard deviation for this estimate. So again, we need this in order to get sort of a distribution. Like we need to get it to a standard normal distribution so that we can carry out a hypothesis testing. We can get our test statistic, right? Yeah, just like in our one sample test that we learned previously, we start with a situation where the population are normal and our variance are known. The variance, I mean this sigma square, sigma 1 square and sigma 2 square are known. We're assuming that for this scenario. And because the populations are normal, both X bar and Y bar would be normal distributed. And we assumed that this two sample, actually the two populations, they are independent. In the sample, they are independent. So that when we combine them, like take the difference of these two, it will still be normal. And we know its mean and its standard deviation. And we just standardize this estimate, X bar minus Y bar, by minus its expectation and divided by its standard deviation. We standardize this so that this Z here would be a standard normal with mean 0 and standard deviation 1. Now we have our test statistic Z. So let's give the formal structure for our two sample test. If we use this delta 0 for the value of difference we are testing, so normally we would use 0 being this delta 0. So delta 0 is often 0, but not always the case. So we will use this delta 0 for to generalize. So this is our null hypothesis. Then our test statistic would be, remember we used this estimate minus its hypothesis mean. So the hypothesis, the value for this mu1 minus mu2 is this delta 0. So normally this would be gone if it's 0. And we divided it by the standard deviation. And the alternative hypothesis, we could have like one-sided test or two-sided test. Just like before, when you have this alternative hypothesis being greater than this 0 or delta 0, then the p-value would correspond to the area under the bell curve to the right of your test statistic. If you have less than something in your alternative hypothesis, it would refer, your p-value would be the area under the curve to the left. If it's a two-sided test, we just sum up the two tail area. Well, to the either is, yeah, let's just use to the right of this absolute value of Z. So it would be 2 times the tail area to the right. So this is the basic structure we're doing for this testing. And I mentioned we can also do confidence interval for the difference of two means. Well, it's actually the same formulation. We just switch the estimate from previously we have this being X bar, but now we are doing this X bar minus Y bar. And we just use the same thing. So this is the same Z value. The probability of this Z value in between the negative Z alpha over 2 and positive Z alpha over 2 being 1 minus alpha. So if this alpha being 0.05, so this probability would just be 0.95, right? And then remember we did some rearrangement in order to get this range for the X bar and for, get a range for the X bar minus Y bar. So confidence interval, confidence interval is for the estimates. So if you know the big structure for confidence interval, you can recognize. So this is your estimate, and this would always be your Z score, like Z alpha over 2. If alpha being 0.05, this Z value would just be 1.96 all the time. And we still need the standard error for X bar minus Y bar, which is of this format. And if M and N, like the sample size, are large, the central limit theorem would say this is valid without the assumption of normality and known variance. So that's what the central limit theorem tell us. Remember, we did assume that we have normal distributed population and known variance, like in the beginning when we set up the test. But if sample size is large, we would have normal, and we can always use this formula for calculating confidence interval. So this is the confidence interval, and we talked about previously, it's the z-test, two sample z-test, and confidence interval calculation. Now let's look at the t-test. That is for still normal population, but this should be unknown variance. I should correct it. Well, the slides have not been posted on Blackboard, but I will correct this before I post it so that you have the correct version. So now we move to the more realistic situation where we could have small samples. And still we're assuming we have normal distribution, but we have unknown variance. So this is for unknown variance, we use t-test. And again, because we said the populations, small samples population, where the samples come from would be normal, then X bar, Y bar still be normal distributed. And we still do the standardization for this X bar, Y bar by minus its mean and divided by its standard deviation. Then we have this following a t-distribution. Well, you might notice this standard deviation is changed by this S1. We use this sample standard deviation to replace the true standard deviation sigma 1 and sigma 2. So now we have S1 and S2 being the sample standard deviation. Well, for this one, you have to pay attention. Well, the t-distribution here, because now we have two samples, right? Previously, when we have only one sample, the degree of freedom is just n-1. But now we have two samples, and we will use a formula to estimate this degree of freedom, nu. And this is the formula for estimating nu for this t-distribution. Well, it looks a bit complicated, right? Remember, this SE is actually your sample standard deviation divided by the square root of your sample size. So this SE is not S, so they are different, okay? So you have to plug in the right value in order to get the right degree freedom estimate. And also we would round this new down to the nearest integer. So if you get new equal to say 7.9 by using this formula, we would use new equal to 7. So we would round this new down to the nearest integer. We need this new because when we try to get the p-value or get a t-value in R, we would have to supply the degree freedom, right? Okay, and the structure for t-test would be just very similar to the z-test we just went through. So the null hypothesis would be still the same. Well, the only difference is that we use this S1 and S2 instead of sigma 1 and sigma 2, because we said this is for unknown population variance. And these are all similar as previously. Well, an extra step for this test statistic is that you have to calculate the degree freedom, right, in order to get a p-value. Okay, and how to get the p-value is just like the same, but now you are using a t-distribution instead of a normal distribution. Okay, and oh yeah, confidence interval, very similar, right? You can tell that it's the same structure. Only difference is this S1, S2 instead of sigma 1, sigma 2. And we have this t-value, t alpha over 2 with this degree freedom, where we have to get this t-value from R. You will see an example soon in R. Yeah, here let's go to R. Oh, this is the example I get from your e-textbook, which is on Web Design. For this one, okay, I copied the, well, I think I have the book open. Oh, this is for the next example, but this is the first example, which is example 9.1. But I copied this problem statement, yeah, from the textbook. Okay, so let's take a look at it. So analysis of a random sample consisting of 20 specimens of cold rolled steel to determine yield strength results in a sample average strength of 29.8. So this is information about one sample. Well, now you can write like the sample size for the first sample is 20, m equal to 20, and sample average strength, so that's your x bar, 29.8. And the second random sample of 25, two-sided whatever steel specimens gave a sample average strength of 34.7. So this is your second sample information, where the sample size n equal to 25 and the sample mean y bar, sample average y bar mean being 34.7. And we're assuming that the two yield strength distributions are normal, with sigma 1 being 4 and sigma 1 being 4, sigma 2 being 5. So this is corresponding your first sample and second sample. So now we know the population variance, population standard deviation, sigma 1 being 4 and sigma 2 being 5. always pay attention what is given to you. It's the standard deviation or it's the variance. Right, now we have the variance here. That means we have to do the square it when we plug in the formula. It's asking, does the data indicate that the corresponding true average yield strength, mu1 and mu2, are they different? So this is basically like apparently two sample test, and is asking if mu1 and mu2 are different. That means our parameter of interest is mu1 minus mu2. And we are going to measure the difference. And so our delta 0 will be 0 in this case. And the null hypothesis is just mu1 minus mu2 being 0, while the alternative is not equal to 0 because it's asking, are they different? It's not asking, are they like, if it's asking like, if mu1 is greater than mu2 or mu1 is less than mu2, so that would lead to a one-sided test. But here is a two-sided test. Well, if we just input our information, get it from the problem statement, we defined m, n, x bar, y bar, and so this is my sigma square 1, sigma square 2. Okay, I take the square of the sigma 1 and sigma 2 already here. So now we need to get our test statistic, where we use this estimate x bar minus y bar minus the hypothesis value for mu1 minus mu2. So that's 0 divided by the standard error, so which is the square root of sigma 1 square divided by m plus sigma 2 square divided by n, and take the square root of this summation. And we can get a z value being negative 3.65. And this test statistic is more than 3 standard deviations below what we expected to see if the null is true. Remember, for standard normal, the standard deviation is 1. So this negative 3.65 is more than 3 standard deviation away. So if we want to calculate the p-value, this is the formula where, because this is a two-sided test, it's like the summation of two tail areas. So we just use 2 times one tail area, whether it's either on left tail or right tail. It actually doesn't matter. So this would be our p-value, which is really small, so that we can reject the null hypothesis that the difference being 0. Okay, so this is our first example. Let's take a look at another example, which is this is hiding. How do I get rid of this thing? It's hiding my. Okay, there we go. This is the. Okay, I'll just put it here. This is example 9.5, which is also a 2 sample test, but we are interested in a confidence interval. Let me enlarge this a little bit. Yeah, so this is a statement. We are basically comparing the control group and experiment group or treatment group. It's giving you like the sample size directly. You extract the information directly from this table. Well, if you are interested, you can take a look at what exactly is measuring and is comparing. And well, this one is easy. You just get sample size, M and N, sample mean, X bar, Y bar, and S1 and S2, because it's a sample standard deviation, right? So it's S1 and S2, not sigma 1, sigma 2. And in this case, because we do not know the population standard deviation, we only know the sample standard deviation, it's a hint that we have to use the confidence interval formula for t distribution for, well, let me come back here. So we would have to use this one, like use the t value instead of z value, because you know only the S1 and S2, but not sigma 1, sigma 2. Okay, so yeah, so this is what it looks like from the problem, and your homework question would be, some of them would be just like this. Just take information from this table. Yeah, we get the M and N equal to 50, and we define our X bar and Y bar. Yeah, X bar and Y bar, and S1 and S2. Do not switch, do not switch the order. Like this S1 is for X and S2 is for, oh, well, it actually doesn't really matter because you're taking the summation here. But X1, X bar minus Y bar, you cannot change this, right? Well, anyway, we defined our all the information we need for this formula. And we're interested in get a confidence interval for this X bar minus Y bar. And a significance level being 0.05. Yes, this is, yeah, the previous one have a significance level being 0.01. But anyway, this p-value is less than that. This one we're using alpha being 0.05. And let's get this z value first. Remember, this is the formula we use to get this z score. And actually, yeah, I mentioned if we're using 0.05, the z value is about 1.96. So this is just kind of checking. It is 1.96, right? And plug everything in. Well, you can do it this way. So this is, I'm showing you, if you are lazy, that you do not want to assign those variables one by one, you just want to directly plug everything in. Like you have write everything down on your paper and you just plug in, or you write down the whole formula on your paper. You just input your formula into R and use it as a calculator. And this is how you get the confidence interval. But if this alpha is different from 0.05, you might have to use this anyway, use this function anyway. And this is how you get your confidence interval. Well, for this one, we have to, yeah, we will, if you still remember, the confidence interval have a correspondence with your hypothesis testing. So for example, this one, if we're testing, if mu1 minus mu2 being 0, see our null hypothesis is that, and we get this confidence interval, they are all negative, like this is negative 4.8 to negative 0.5. So the whole confidence interval is less than 0. That means if you do a hypothesis testing with this, with the null hypothesis being mu1 minus mu2 equal to 0, you will get a rejection of the null hypothesis. with this significance level being 0.05. So yeah, just by looking at this confidence interval you got, you can guess, you will know what your hypothesis testing would be in that case. So this is the correspondence between confidence interval and hypothesis testing for two-sided test. Yeah, so we can use this interval to be very confident that there is a difference between the two experiment groups, the experiment group and the control group, as the interval does not contain 0. So that is, we would reject the null hypothesis that mu1 minus mu2 equal to 0. Okay, so this is the confidence interval and the correspondence to hypothesis testing. Well, we have another example. Let's just go back to our textbook. Okay, we'll need to use this 9.6. I remember it's not far. It's, yeah, it's right here. So again, whatever it's working on, it's focused on for this question, let's just focus on this table directly. Apparently, two samples giving you the sample size, sample mean, and sample standard deviation. Well, now we're doing, previous one, we're assuming, let me see. Oh, yes. Okay. So previous one, we are using this normal population, but not unknown variance. Sorry. Oh, that's still a Z. Well, yeah, we're still using a Z value, not a T value here. That is for, yeah, that is for this case. So, well, I think this is when we have large enough sample size. That's why we could use this formula. Yeah, I think I forgot to mention, like M and N, because they are large, we can still use this, even though we only know the sample standard deviation. Remember, yeah, for this one, we only know the sample standard deviation S1 and S2. But we can still like use this Z value because we have a large enough sample size so that it's still following a normal distribution for the Z value. I mean, for the Z test statistic, if in the hypothesis testing setting. So similarly, when we calculate confidence interval, now we know it's still a normal distributed data. We can use this Z value instead of T value. So this is the difference of this example 9.5 and 9.6. So pay attention, your M and N in this example is 50, which is way larger than being 10. So I think a general rule of thumb for small and large enough sample size for that normal assumption would still be, I think still be, if it's greater than 30, you can do this Z instead of T. But if you have not big enough sample size and you do not know the sample standard deviation, population standard deviation, you will have to use the confidence interval and hypothesis testing with a T distribution. Yeah, let's work on this one. And extract all the information from this table. Well, I think I put everything here. Yeah, sample size, the means for 2 samples and their standard deviations. And we're assuming the 2 populations are both normal, but because we have smaller sample size, we would have to use that t value instead of z value when we do the confidence interval. And because we're using t, we have to estimate the degree freedom nu. Remember, we are using this big formula for this degree freedom estimation, and we first need to get the SE1 and SE2, where this SE is the sample standard deviation divided by the square root of the sample size. So this is what we are doing here. We're using the sample standard deviation divided by the square root of the sample size to get SE1 and SE2, and we will use these two to plug in the formula. So when you work on the homework, you can use this as your sort of your template. You just plug in different values and use this formula. Yeah, this SE. So for the denominator, if you pay attention, this SE1 to the power of 4, because, oh, well, I used it, SE1 to the power of 4. So, oh, never mind. So this is the new, the estimation for degree freedom. And we get 9.86 something, and we round it down to nu equal to 9. So we have degree freedom being 9, and we can use this to calculate our t value. To calculate the t value with this function in R, and degree freedom specified, and plug in the alpha significance level, and lower tau being true. So, well, yeah, lower tau being true will give you the left side of your the area under the curve to the left of your t value. And next, you just plug in everything in the formula, and in order to get your confidence interval for this x bar minus y bar. Okay. Yeah, I think that's all I need to illustrate for, yes, for this two-sided t-test. Confidence interval. This is from this one. Okay. Well, so for the two-sided test, two sample tests. Previously, it's called unbiased test. Now let's take a look at what is a paired test. So basically, we would have paired samples. So for the pair test, we are focused on like a set of n observations, but with 2 measurements for each observation. So previously, one sample have m observations, one sample have n observations. So they could be of different size, right? But here we have only n objects, like n elements, and things. We're measuring them basically twice, or like 2 measurements for each element, each observation. So it could be like the measurements before or after something, or the left and right side of something. So in this case, the data is paired. So now we would have the paired value being x1, y1, x2, y2. So they are pairs. And in total, we have n pairs. And again, we're still assuming the expectation of x one, it should be x1 here, and the expectation, oh sorry, yeah, xi, because I goes from 1 to n. The expectation of yi is mu2. And now we focus on their difference. I mean, like the pair difference. I should say pairwise difference. And we define this di being xi minus yi. And we're assuming this di, they are normally distributed with mean mu d and standard deviation sigma d. And the change is that x and y, they are no longer independent because they are paired up. We are measuring, well, the same thing before and after, or like we're taking two measurements for the same thing, x and y. So the two measurements are no longer independent. So the independence assumption is no longer valid here. But we use the independence of x bar and y bar to compute the variance of this, the difference of them. Okay. So now we're focusing on this di, right? From two samples, paired samples. Now we have only like, if you think it in terms of data, now we only have one vector of data, which is the di. And we will get the mean of di, the mean of d, mu d being mu1 minus mu2. Or this one does not require the independence assumption, because like ex minus y would always be ex minus ey. And we have that d is a normal random sample with mean mu d, and so we can do now we basically get back to one sample test, and we do not know the standard deviation. We'll do a t-test. Now it's a one sample t-test with n-1 degree freedom. Okay, so or in this case, the null hypothesis would be focused on this mu, this should be mu d, sorry, like too many typos here. So this is mu d equal to this delta 0. So delta 0 could be 0, could be something else, some other values. Mostly it's 0. So the test statistic would just be this d bar minus this delta 0 divided by the SD, which is the standard deviation for the data d, which is the difference of the two samples, two samples, divided by the square root of n. And now n is the sample size. If you just think it in terms of like we have only n elements in the experiment. So for example, we have n patients, we take the measurements of something before and after some treatment. So we have n people. You just do not think it, we have like 2 times n of the size data. Or you can think it, we have only n objects. So the sample size is n. Well, now it's one sample t-test. You're supposed to know what it is already. The assumption here is that DI constitute a random sample from a normal difference population. So we're measuring the difference of, like, we're thinking it's one sample, but it's measuring the difference. Okay, and well, I think this is not hard for you to carry out a one sample t-test. But it might be, okay, we're not at that point yet. Okay, let's talk about the confidence interval for a moment, because this is also like old knowledge where we just plug things in because we know this is a t distribution already. This test statistic is following a t distribution with degree of freedom n-1, right? And for the confidence interval, it's the same thing. You just use this t value times the standard error of this d bar. And this is the formula for the confidence interval. Well, when n is small, the validity, well, I'm not sure how to pronounce it, of this interval requires that the distribution of the difference to be at least approximately normal. So if n is small, but if n is large, we can still use the central limit theorem that we have the corresponding z interval would be valid without any restriction on the distribution of the difference. Okay, so this is when n is small, but when n is large, still that we're talking about paired test and paired confidence interval. If we have a large n, we can just use a z interval, which means you replace this t by a z value, z alpha over 2. Okay. Oh, this is for the t paired tests. The most difficult thing for this section is that when you carry out the experiment, should you use a paired test? Like, should you do a paired experiment or you do a unpaired experiment? So that is like unpaired is what we talked in the very beginning, the previous section. So, well, basically the guideline, we have that later here, but the difference where when you use a paired test, you pay the price by reducing the degree of freedom. So if you use the paired test, if you do a paired analysis, you are getting a smaller degree of freedom. Well, what the result of the smaller degree of freedom is that it will increase your type 2 error when you have the type 1 error fixed. So if we have the significance level alpha being fixed, we would prefer large degree of freedom because large degree of freedom would decrease the type 2 error. Well, when you do a paired analysis, you reduce the degree of freedom. So the type 2 error increased. So the basic guideline to decide if you should carry out a paired experiment or not, you should focus on the study itself and the objects you're doing the experiment. So yeah, the experiment unit. So if they are relatively homogeneous, so they are very similar, your experiment unit are very similar, and the correlation within pairs is not large. So your xi and yi in our pairs, their correlation are not big. That case, you should use independent sample experiment. So that is unpaired experiment. But if they are not very similar, there is great heterogeneity between the experimental units, and you have a larger correlation within pairs. So xi and yi, if you calculate the rho, the correlation, it's relatively big, then you should do a paired experiment. So, well, this is probably the key thing when we talk about paired experiments or unpaired experiments. But it's easy to distinguish if you should use like formulas for paired or unpaired, because when you see something like the measurement is before and after something, that is a paired test or a paired intervals. Or like we're doing like medical experiments on twins, like for twins, they are like paired, right? Yeah, some other keyword would be before and after something, or it can be yeah, control and experiments. Yeah, it could be control and experiment. Well, normally, yeah, before and after would be the keyword for paired tests. For the unpaired test, it could still be control and experiment. Well, yeah, so this is, I think this concludes our today's lecture. And I didn't give examples, like our examples for the paired test and interval, because it's basically the same thing when we do hypothesis testing. Like one sample tests and confidence intervals. Well, I think that just concludes our lecture today. And the homework will be available midnight of today, and I will correct those typos on my slides and post it on Blackboard. Yeah, if you have any question, let me know. And again, yeah, we mentioned in the beginning of our lecture, final exam will be December 9th. You have the whole day to pick whenever to start your exam. You will have 2 hours and 45 minutes to finish it. Yeah, it will be on level sign. Oh, from now on, you will have only, after this homework, you will have two more chapters which have homeworks. Yeah, I guess that's it for today. I will see you next week. Yeah, I think next week we should have face-to-face lecture, depend if there's no like weather issues, other issues. Okay, I will see you all next week. Okay.